This is muscle video number 11, and this is the second of our action potential series. Here are our learning objectives. Number one, what is the difference between these two types of ion channels? Keyword here is that they're ions. There's ligand gated, also known as chemically gated channels, as well as voltage gated. And number two, describe depolarization and repolarization within an action potential. Now, we used those terms in the previous video, repolarization and depolarization. We also used the word hyperpolarization. And now we're going to use those words in the context of an action potential itself. Number three, where is the action potential generated, and what does it actually mean for this thing to be propagated? To start off, let's remind ourselves of something like this. What we have here is a phospholipid bilayer. There's my cell membrane, and this is the outside of my cell. There's the inside of my cell. And these little red dots all represent polar molecules. So you read the description here. A polar substance is more concentrated on the outside than the inside of the cell. So I copied and pasted our little sodiums that we used in the previous videos. And so sodium here would be the same as these little purple dots, or red dots. They look red. So these red dots are sodium. So where do we see a higher concentration of sodium? Again, these red dots being sodium. On the outside or inside? Well, it's the outside. So again, this is consistent with everything that we know. So the question then becomes, can this charged polar substance then easily permeate through the cell membrane? And we've already established previously that it can't do that unless there's a door, unless there's a channel. And this thing right over here, it's the same as this guy. These things are the doors or channels that I've been talking about. So what we see here then is that sodium itself wants to actually pass through these doors, but in this case, it is in a closed state, and here it's in an opened state. So the question is, how do we get this thing to go from a closed to an open state? It's no different from, how do you open your front door? Whether you've got like a little thumb trigger thing or a door knob. The point is, there's some mechanism that you have to initiate to open the door. If you want to open the windows in your car or in your bedroom, then there's some mechanism that you have to take advantage of in order to open those things. So it's no different here. I've got a door or a channel here, and that's closed. And the question then becomes, how do I open that? And the reason I want to open it is that I want to let sodium to pass through to go down his electrochemical gradient. Remember, he wants to go down his electrochemical gradient. He wants to reach equilibrium, but he's not able to do so unless that door gets open. So how do we do it? Well, we have some sort of signal molecule. It's written here, stimulus molecule. And that stimulus molecule then binds to this particular binding site. So he is going to come and he's going to attach right over here. And that's what we see over here. And once that happens, that is the trigger that allows opening of the door. And so now that polar substance can diffuse across the membrane. So without this stimulus molecule, whatever that stimulus molecule is, maybe it's a neurotransmitter, maybe it's a hormone, maybe it's some other paracrine coming from neighboring cells. The point is that stimulus molecule comes from somewhere, and he comes on down and he binds to this channel, and that's what allows these doors to open up. Now, if we were to go back and revisit this slide that we saw earlier, then you'll see that, well, there's my neuron, remember my nerve cell, and this is the rest of my muscle. And so remember what we did is that we zoomed in, and we looked specifically at this part, and that part is going to be right where the nerve, why can't I move this? Right where the nerve goes up to the muscle membrane. And see these little blue dots? These little blue dots there are a chemical named acetylcholine. That's what ACH represents. You need to know that name. The name is acetylcholine. And so acetylcholine then diffuses from here to here, and it binds to stuff over here that we can't see. But if you could see, if we could zoom in even more right in that section, what we see is, we would see this. So we would see that thing that I just showed you, and that, let me try to line me up again. So that image that I just showed you, this one, where this chemical would be those blue dots. It diffuses across. It came from a nerve, and there's my nerve right over here. Imagine my nerve right over here. So my nerve comes here. It spits out this acetylcholine, which then comes along. It binds to this receptor, the binding site over here on my channel, and that triggers the opening. And now sodium can go from out to in. So the key point here is that, yes, you do have these channels, but we got to find some way to open these channels. So what was the trigger here to open this channel? The trigger here was a chemical. And because acetylcholine is a chemical, we refer to this as a chemically gated channel. Again, this is a chemically gated channel because the chemical opens the doors. It's a chemically gated channel. The other name for chemically gated channel, as I showed you in your learning objectives, is ligand gated. So chemically gated doors or channels and ligand gated, they're the exact same thing. It doesn't really matter which term you use, but both are used commonly out there, so you should know both terms. And so right over here, you have chemically gated channels, if you were to zoom in and see that thing. Now, let me ask you a question. Something I'm going to introduce now and we'll tackle a little bit later on, is that these blue dots, do they go all over the skeletal muscle, or do they only go to this particular neighborhood, meaning this little patch of cell membrane, or do the blue dots go everywhere? Well, the blue dots, acetylcholine, only stay put right over here. And so this section of the muscle cell membrane is specialized because it is the only area that can receive these acetylcholine molecules, these chemicals. And so this guy has a special name, and his name is the motor end plate. So we call this guy over here the motor end plate. What is motor end plate? It's the specialized portion of the skeletal muscle membrane, cell membrane, that has receptors for acetylcholine. You'll notice all these other places don't have those receptors. Okay, so now let's come back here to this picture. So we've just established that when you look at this picture, the question becomes, how do I open that door? And we've answered the question. You throw chemicals at it, and if the chemical opens it, we call this a chemically gated channel. Now, there are other channel types out there. So if you looked at the learning objectives, I'm asking you to know the difference between these two types, the chemically gated channels and the voltage gated channels. And so that already tells you right off the bat that there are different types of ion channels present. So this slide is showing us different types of ion channels. Here's my chemically gated channel. This is my neurotransmitter, acetylcholine, coming through. That opens the door, allowing sodium to come through. If there is no neurotransmitter present here, then the door is closed, and you see that sodium itself, it looks like it's just bouncing off here. There's no way sodium can get through. There are other types of channels. Some of them are mechanically gated. We're not going to talk about those because they're really not present in the skeletal muscle fiber. But really what that means is that these doors open in response to pressure here on the cell membrane. You have some doors that are always open, and these there's no gate, so to speak. There's nothing that closes these things down, so they're always open. And in previous videos, I talked about how even when your doors and windows are closed in your home or your car, there's always just a little wee bit amount of air that gets through. It's not a perfect seal, and so these cell membranes are similar in the sense that let's just make up a number. Let's say that out of 100 sodium ion channels, a bunch of them are chemically gated, but then there's always going to be 4 or 5 of them that are always open. So in other words, sodium can't come through in waves because most of them will be chemically gated channels, but a little bit of sodium is always going to get through because there are some of these so-called leakage channels that are open. Now, the one that we really want to contrast here then is the chemically gated versus the voltage gated. So how do voltage gated channels open? Well, the way voltage gated channels open is to zap them, and that's what I put this lightning bolt here for. And so the way you open up these guys is to give them a jolt of current. So when you change the electrical properties of this cell membrane, so listen to what I said again, when you change the electrical properties of this cell membrane, then this door opens. Now, right now is probably a good time to remind you that what we have here is the inside of the cell membrane, keep in mind, has a certain membrane potential, right? And that's negative 70 millivolts. So what I will tell you is that at negative 70 millivolts, these doors are actually just hardwired to stay closed. That's just the intrinsic wiring. On the other hand, if that membrane potential now changes and the change is sufficient, then these doors will open. So the question becomes, like, how much do I have to change? What if I'm at negative 65? In that situation, I've dropped by 5 millivolts. Is that sufficient to open the doors? It's not. What if I dropped a little bit more? I dropped now to negative 70 millivolts. Is that sufficient to open the door? And the answer is still no. The magic number is negative 55. Now, why negative 55? That I couldn't tell you. It just is what it is. These things are hardwired to start opening up at negative 55 millivolts. That is the magic number for opening of this. So if, on the other hand, I hyperpolarize and now I'm now at negative 90 millivolts, these things will be closed, of course. Why? Because they're not wired to open there. Again, what's the magic number? Negative 55. That is the number at which they open. So To review, then these are chemically gated or ligand-gated channels. They open in response to a neurotransmitter. What is our neurotransmitter of interest? Our neurotransmitter of interest is acetylcholine, right over here. And these ion channels over here open in response to, though I said zap, what I really mean is a change in voltage or change in membrane potential. And so you'll notice even the units here, millivolt. And so when the voltage itself is changed to negative 55, that's when these doors start opening up. All right. So now let's look at this. The two types of ion channels we care about are chemically gated and voltage gated. We've already said that. Chemically gated channels open in response to chemicals, and specifically we care about acetylcholine for our purposes. Voltage gated channels open in response to changes in voltage, and what we really care about here is when I go from negative 70 millivolts to negative 55 millivolts. That is the big change that needs to occur in order for us to open up voltage gated doors. Now leakage channels then are always open. And again, there's not a lot of them. Don't think that they're all over the place. There's not a lot, but they definitely are there, and we got to be aware of those. All right. So now that we have a grip on the different types of ion channels, let's actually look at an action potential. This is a set of numbers that are really important to know. A muscle rests at negative 70 millivolts. A muscle, specifically the motor end plate. Again, what's the motor end plate? The motor end plate is this little patch of skeletal muscle membrane. That's the motor end plate. The motor end plate depolarizes slowly until it hits threshold. And it depolarizes when sodium doors are opened because of acetylcholine. And where did the acetylcholine come from? It came from the nerve. And once you reach threshold, now, what is threshold? Threshold is negative 55. Remember how I told you that the magic number here is negative 55? Well, the term that's commonly used for that, we say that is threshold. So you've all heard the term threshold before. The question then becomes threshold. Threshold for what? And in this case, we say, oh, it's the threshold for opening of voltage-gated ion channels. Once you reach... one more time. Threshold for what? It's threshold for opening of voltage-gated ion channels. Voltage-gated ion channels. And I will just tell you right now, when I say voltage-gated ion channels, I mean both sodium and potassium. Okay, both of those are involved here. So, from there, once you reach threshold, you continue to depolarize rapidly until you reach sodium equilibrium potential. You remember that number, and that's plus 35. And after that, you repolarize rapidly and go back to rest at negative 70 millivolts. So that's just a big list of, like bullet points. So let's look at it graphically. When you look at this thing graphically, here's what we're looking at. My skeletal muscle fiber is now sitting at rest. It's sitting at negative 70 millivolts. And what we're about to see, this entire thing is called an action potential. So right now I'm sitting here at rest. Okay, I'm sitting here gladly, happily at rest. And if nothing happens, if there's no acetylcholine, there's no stimulation, then this purple line, this would be time on the x-axis. This purple line stays at negative 70 millivolts because nothing's happening. On the other hand, if I now stimulate this muscle fiber, what we're going to see is that the electrical property of the motor end plate goes from negative 70 millivolts. Once I let acetylcholine bind and do its thing, sodium will start trickling in. So one more time, what am I talking about here? I'm talking about right now, at the motor end plate, I'm at negative 70 millivolts right over here. Once acetylcholine binds, sodium itself will now start trickling in. Once sodium itself starts trickling in, well, you know this from the other videos. What happens? Well, I'm here at negative 70 millivolts, right? So a little bit of sodium comes in, and now I'm at negative 69 millivolts. And then a little bit more comes in, now I'm at negative 68 millivolts. And, millivolts. And then I let even more sodium come in, and now I'm at negative 55 millivolts. Ding, 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 okay? But what you see is that I've begun to depolarize that cell. So this is my depolarization that I just showed you, negative 69, 68, 67, 66, 65. And once I hit threshold, what happens here? Opening of voltage-gated sodium channels. And when that happens, sodium floods in. Instead of trickling in drop by drop, it now floods in. Well, why does it flood in? Well, here's why. I'm going to tell you, I'm just going to make up a number here, that along the skeletal muscle membrane, especially at the, not especially, but at the motor end plate, I'm going to say that we've got 5 of these chemically gated sodium channels, but then 100 voltage gated channels, just right next door, just waiting. So the 5 sodium channels open, allowing sodium to come in bit by bit. But once I hit negative 55, all those 100 sodium channels in that neighborhood now slam open and sodium floods in. So that's why this line is so steep. So sodium rushes in very, very rapidly, and I rapidly depolarize to positive 35 millivolts, which is sodium equilibrium. Now from there, what we're going to see is that those sodium doors will now close. The chemically gated sodium doors will close, the voltage gated sodium doors will close, and when that happens, I also am going to see opening of voltage gated potassium doors. So when voltage gated potassium doors open, I now start to repolarize because potassium now starts leaking out, going from in to out, making me more and more negative, right? First, plus 34, more potassium leaves, plus 33, more potassium leaves, plus 25, more potassium leaves, plus 15, more potassium leaves, 0, more potassium leaves, negative 10, more potassium leaves, negative 40, so on and so forth, until I overshoot just a little bit, and then I come back to resting membrane potential, because by then, potassium doors have closed. So one thing that I want you to think about when you consider these doors is that I'm giving you mechanisms for opening, right? A chemically gated sodium door opens here. A voltage gated sodium door opens here. A voltage gated potassium door opens here. And here I'm now back at rest. So that answers which door is opening and closing. And when you think about these doors, everything that I've said, I haven't given you a signal that says, and this is what makes doors closed. I've only said to you, this is how you open a door. Well, the reason we don't have to talk about closing is the closing of the doors is automatic. You can think of these ion channels kind of like these swinging doors. Look, you need to apply a force to open this door. If I want to walk into this room over here, I push on these swinging doors. But when I'm in that room, I don't need to push them backwards. You know that. You've all seen doors like this before. Why? Because of the way these doors are designed, once you push them to go in, a moment later, whether you like it or not, they're going to end up closing. That's just how these doors work. And the ion channels are no different. The ion channels only stay open for just a moment, and then whether you like it or not, they close, unless I go stimulate them again. Meaning that if I walk through and the door starts coming closed, but another person comes in behind me, then of course the door stays open. But left to its own devices, once you stimulate it once, the door will open and immediately close. And that's why we see closure here. So to rehash this section, what we see then is at point A, I have opening of chemically gated sodium channels. Sodium starts trickling in. At point B, I've hit threshold. I see opening of voltage-gated sodium channels. And as somewhere along this range, those chemically gated sodium channels will actually close. But my voltage-gated sodium doors open here, and I spike up my membrane potential all the way up to point C. At this point, my voltage-gated sodium doors close, but my voltage-gated potassium doors open, which allows potassium to leave, allowing me to repolarize all the way back down to resting membrane potential. Okay, so that answers which door as well as which ions are moving. So now, the last thing that I want to mention here is this question. What is threshold for opening of voltage-gated sodium doors? Well, you already know that threshold, right? That threshold was negative 55. But here, I told you that the threshold is negative 55 for opening of potassium channels as well, too. Voltage-gated potassium channels. But yet, on this slide, I'm telling you that potassium channels are actually opening here when it's at plus 35. So what gives? Well, here's the answer. Voltage-gated potassium doors open at negative 55. But let me just hear me out. When voltage-gated sodium doors open, they open immediately and quickly and entirely. When voltage-gated potassium doors open, you're basically signaling them to open here, but it takes a little while for those doors to creak open. So at point C, this is the point where potassium doors are now open, allowing potassium to move. But the trigger for opening them was actually -55, okay? So the reason voltage-gated potassium doors open later than voltage-gated sodium doors is simply because they open more slowly, but the trigger is the same. All right, let's rehash a couple of things. There's some more things I want to do, but I want to cut off this video. We talked about the difference between the two types of channels, ligand-gated channels, voltage-gated channels, as well as those leakage channels. We described depolarization and repolarization of action potential. When you get more and more positive, that's depolarization. Let me say it differently. When you get less and less negative, that's depolarization. When you get more and more negative, that is repolarization. If from -70 I were to shoot even further down, that would be hyperpolarization, but simply coming back down to rest is repolarization. And then we talked about, we just did this. And then where's the action potential generated? Where is it generated? It's generated at the motor end plate. And what does it mean for it to be propagated? We're not quite there, so we'll get that. I have a couple more things I want to say about action potential as well as propagation, and we'll do that in a follow-up video.